Alright, what's up everybody? This is Vexor and welcome to another episode of Let's Make a PID Loop. Alright, so say that your robot has two motors on the left and two motors on the right. The issue is that the motors are only $15 each, and of course you can't expect the Vex motors, either 393 motors or 269 motors, to have too much the quality to be too consistent, which means that probably on the left side you might have two motors that are a little bit weaker. On the right side you might have a stronger side, so that when you give the base the same value, the right side might be a little bit faster than the left side, which is not quite an issue in the short run, but in the long run, if you want to say go a really far distance, then probably your robot will go like slightly in a swing turn position because the right side is a little bit faster than the left side, which is which is very bad. Because when we are doing this PID base controller, we are assuming that the robot goes in a straight line, and we do want it to go a straight line. And the reason at the beginning we used two encoders is that we kind of want to try to even out this issue, because we were like, alright, even though my right side goes a little bit too much and my left side goes a little bit slightly less, I still use the sum of it so that I still get a fairly average value of the right side of the left side as my error reading. Which evens out the issue a little bit, but we don't want the swing turn or getting off track at all. And so today we are going to discuss how we're going to fix that issue. So essentially, think about things like this. We are going to add on another part of the program called error correction, which basically means that if with the two encoders I monitor the right side of the base, the right side base reading, I'm the encoder on the right side, that reading is greater than the reading on my left side, that means that my right side is going too fast. Therefore I somehow need to slow down my right side and boost my left side a little bit. And that's essentially another PID error correction, but in this case, in my case, only using P in this case worked well for me. It's just basically slight correction. And in this case, if we are actually going to write the program, I assume that the P constant is going to be very small. So this is just an optional add-on to your PID controller. If you say that I trust my base and I tested out my motors, I'm sure my motors will make the base go straight, then of course you don't have to include this. But if you feel that your base always kinda gets off track and goes in arc, then it's very nice to add on this part of the program. Alright, so let's start. So first, we need, in order to do this, we need to send the values separately to the left side of the base and the right side of the base, so that we will have to create some more user functions so we can more easily navigate to that. So move right base. So the first is moving the right side of the base, move right base, and we are just only going to keep the move right base. That's how you move the right side of the base. Just setting these basic things up. And then we have move left base. So we are only going to leave the left side base on. Alright, so we're done. And for the main PID algorithm, we are not going to change that. We're still going to calculate that. But it's just after we do this PID calculation algorithm, after we calculate this and then we limit this, we do an additional calculation. We do an additional calculation such that we check whether the right side is too big or the left side is too big, so that we need to create some more constants. Some more variables. We are going to put the variables here. First, we need a float. We need another p value. We need another p constant. However, it is error correction, so I'm going to just put it as kpc. Equals to probably very small, 0.01, I guess, because we don't want the robot to be wiggling all the time with this addition. We just wanted to somehow correct the errors, or somehow try to even out the errors, and we don't even want to we don't even want any overshoot in this case, so we'll just keep it small. So we got this, and we have a float, error, integer, which is the we call it error drift. And the reason these things are popping out is that I have my little Skyrise program in here as reference, just in case I forgot about something. And this is just to let you see what I did in Skyrise. Good old program, 2,000 lines of code. All right. So I'm going to put hopefully in the future I'm going to put those things into bite-sized chunks, and I'm gonna make videos about all of them. So in the error drift, we have a drift error reading, and then we have a actually this is good. Actually, let's just do this. Let's do another float. Proportion drift. All right. Think that is it. Is that correct? Yes, that's correct. All right. So let's go ahead and set up. So what is our error drift? Think about things like this. If your right side base is too big and your left side base is just basically where it's supposed to be, then the right side will be bigger than the left side, which means that our error would be actually the subtraction of one side of the base from the other side of the base. In this case, I'm just going to keep things simple. Error, and let's do right side subtract left side. Error drift. Error drift is equal to encoder excuse me, where is it? Right base. I believe that's correct, because opening up the other program is kind of messing me up. So yeah, right base. Right base. Actually, excuse me, let me check. Alright, right base. So right base subtract left base, and motor encoder left base. Alright, compile program, see if we made any typos. Not really. Great. Left base. So that's our error drift, and our error, our actual proportion drift, our proportion is equal to, just like a regular PID controller, is equal to the KP, our constant, multiplies our error. And then finally, rather than giving the final power directly to the entire base, we are giving the left side base, we are giving the left base a somehow added or subtracted this the final power added or subtracted this proportion of drift, and the right side of base the other way. So instead of move base, we are going to type move left base, and so we have to think about this carefully right here. So what are we doing in this case? In this case, if our right side is too big, meaning that the right side is just basically sticking out, we want the left side to be kind of boosted, so that we want to add a positive value to the left side base when the right side is kind of too big. So when the error is positive, we want to add the error to the left base's value. So that would be equal to final power plus our error, proportion drift. And the right side of the base is basically the same thing. If the right side is too big, then we want to subtract the some sort of scale down value of how much it's getting too big, so that it's actually getting smaller, so that it slows down and matches the our desired target. So move right base, final power subtract proportion drift. Did I make any typos? Excuse me. Nope, I did not. Alright, so basically that's how you do your error correction. Very simple algorithm, not too bad. if you want to, because I don't think I copied and pasted, so that if you want to disable this feature, you just go directly in here and set this value to 0, so that this feature will just be disabled. And I suggest going in there and tuning this feature, because it is pretty helpful. In SkyRise I use the mecanum drive, and mecanum drive is just going back and forth. It's basically like holonomic drive, especially when you're using a holonomic drive. Sometimes it doesn't go in a straight line, and some sort of error correction to make sure you drive straight is pretty important. Yes, so I do suggest you can disable it, but I do suggest you using it, because I used it and it worked pretty well. It made my autonomous pretty consistent. Alright, so this is what I wanted to show you today. Hopefully you learned something. This is SmartMobX Forever, and I will see you in the next video.